last time we talked about machine learning and how it differs from algorithms. And we explained why in certain cases you cannot use algorithms and you need to rely on machine learning to use the abundance of data at hand to accomplish a certain task. And then we said that those tasks could be under different applications of machine learning, basically. And today we're going to focus on two of the most common applications of machine learning, namely the learning associations and classification, as promised previously. Now, when it comes to learning associations, there's a very well-known problem that can be solved with machine learning, and it's called the basket analysis. Imagine you have a supermarket chain, and as a manager, you want to figure out if there's a pattern between certain products in your market chain. Now, before I jump into the example, let's just come up with one notation here. So this guy right here, the probability, which is denoted using P, of X given, this line right here is a condition, given Y, right? And that is the probability that if item Y was bought by a customer, what is the probability that item X would also be bought, right? So, excuse me. So if you can come up if you can compute that probability, then it would tell you about the association between item Y and item X, and that is the whole goal here, right? So let's just basically talk about it again. So probability of X given Y. Okay? Now, if product Y was bought, what is the chances of product X would also be bought, right? And now, let's call X as chips and say beer as Y, right? So what is the probability of chips given, this guy right here, this vertical line is given beer, right? Say you come up with this number magically, 0.7, right? So the way you read it is that the probability of chips given beer is 0.7. And you might ask me now that, okay, how did you come up with that number? And that is how machine learning works. Machine learning would infer knowledge from your data, and it would basically spit out this number as the probability, as the association between chips and beer, right? So if you have this number outputted using your machine learning algorithm, then you can basically come up with the following rule here, which would be of interest to your boss. If the probability is 0.7 or 0.7t, which is the same, you can describe the following rule here. 70% of customers who buy beer also buy chips, right? So then you can basically, I don't know, like put chips and beers next to each other in adjacent shelves, or say you have a very nice beer brand of beer in your market, and then you would probably send some advertisement about like delicious chips with different flavors that you have just bought to the customers, to the regular customers who are basically buying beer all the time, so that you could earn more money, basically. And there's also one more thing that you can do. You can basically make distinction among the customers, right? And that is this guy right here. So you say the probability of X given Y and D. It means that you're considering this other variable as well, called D. And what is D? It is a set of attributes belonging to your customer. It can be the age of your customer, their height, their gender, their weight, etc., etc. So then you can come up with this kind of notation here that, okay, what is the probability of chips given beer, and say the age equal 38 and the height equals, I don't know, 180 centimeters, etc., etc. Anyway, you got my point. So you can come up with a probability here using your machine learning algorithm that, so that is 0.80, right? So then that would mean that if a customer is 38 years old and their height is 180 and they have bought beer, the probability of them also buying chips is 0.80%, or 80% of such customers who buy beer would also buy chips. And that is called the basket analysis. So that was nice, but there is even one more basically common applications of machine learning that you might have heard a lot about, and that is called the classification. It's super popular, basically. You can use many different types of data and apply classification on it, and basically accomplish a very important task. You can classify images, you can classify electrical signals, you can classify many things, right? But I know it might be a little bit vague at this point, so let's start with a scenario so that we would understand this whole thing much better. Now, imagine that there's a bank, right? And a bank gives out loans. It's basically an amount of money requested by customers who are in need of that money, and then they'll have to pay back that money, usually plus some interest, to the bank. Okay, and when a bank has received an application, a loan application from a customer, they might want to be interested to measure the risk of actually granting this customer with the loan, right? So a customer could be a fraud, a customer could simply be not capable of paying back the money because of certain problems that they might have, or a customer might just be basically a very good one, and they might have, but they might be rich and they might have no problem with paying back the money. They simply need the money at the moment, right? So we have a bank, and the bank wants to measure the loan risk. So basically they want to classify their customers, hence the word classification. So they would like to figure out if a given customer who's applied for the loan is a low-risk customer, right? Meaning that we can easily accept their application and grant them with the money, or they're a high-risk customer, meaning that they are going to default on their loan, meaning that they're not going to be able to pay back the loan that we will give them. Now, in order to simplify this problem, let's consider that for each customer we are interested in studying their income and their savings, which have a lot to do with a customer's capability to pay back the loan, right? Because they will describe their financial status, condition, basically. Now, here, the green pluses and basically denote the low-risk customers, and the red minuses, they would describe a high-risk customer. Perfect. And if we look close enough, we can see that we can separate these two sets of customers, right? Using two vertical lines. And I'm going to name each one of these lines where they intersect the axes using these letters. So theta 1 right here is the value for the income, and theta 2 right here is the value for the savings. And using this simple plot, we can come up with a simple rule, and that is exactly what machine learning does. So if the income is higher than theta 1, now what does it mean? So you have to ask yourself, which side of this whole plot applies to this particular part here? If income is higher than theta 1, right? So this is theta 1. All this area, all of it, is covered by this rule, basically, right? All the points here have this attribute here. It means that for all the points here, we have the income more than theta 1, right? And but you might say that, okay, could this be an enough rule? Would that describe a low-risk customer? Basically, that's not right, because as you can see, there are many high-risk customers who also are in the region that we have basically drawn these lines on, right? So if you cannot claim that income more than theta 1 is a good enough rule for you to classify a customer as a low-risk customer or even a high-risk customer, because that area has both types of customers inside. Right. So then you would need another rule, right? And that is this AND guy right here. You will say that if income is higher than theta 1 and the savings is higher than theta 2, which is this region right here, all of this, right? So this is the region covered by savings more than theta 2, right? And if we want to show the region of income more than theta 1, it would be this region, right? And then we are looking for a region where both of these rules apply, and that is the only region that all of them apply is this region, right? As you can see, this is the only region that both types, both rules basically apply, where we have the same, both colors of the lines that I've just drawn, all of them captured in this region. Now, we can say that if income is higher than theta 1 and, that is a keyword here, savings is more than theta 2, this whole thing is applied to this region, this weirdly shaped region right here. Then you can say that that customer, whoever it is, if they fall in this region, then you can classify them as low-risk customer. Otherwise, if they're anywhere else, then you can classify them as a high-risk customer. Now, so this is a rule, right? This is a rule that you have extracted from the data. Basically, your machine learning algorithm has extracted from the data. Now, if a test data, basically a new data that your machine has never seen before, appears, say, I'm going to denote that with a weird shape, say here, right? Someone has a very high income, right? So it would be here, so theta 3, say, a very high income and a very low, that would be here, a very low saving, right? Now, if you ask your machine to classify this guy for you, it would say that, okay, let me use the rule that I've just learned from the data. Is the income of this guy higher than theta 1? Is it? Yes, because theta 3 is higher than theta 1. So far, so good. And is the saving of this guy higher than theta 2? No, it's not. Theta 4 is not higher than theta 2. It is actually lower than theta 2. So since both of them are not true at the same time, the machine would say, okay, this guy is not a low-risk customer, but they are a high-risk customer, so they will classify them as high-risk. Now, the data that we used for extracting this whole rule right here, all these data, all these green and red points on our plot, they're called the training data, right? We use the training data to extract a rule, And those rules are these vertical, this vertical and this horizontal line right here, extracted by the machine. So we use the training data to extract these lines or these rules, which are also called the discriminants, using the training data, right? And then when the model has been trained, you will basically test it with a novel data, a data that it has not seen before, where the actual job of prediction would take place. So the prediction of what exactly? The prediction of the class, right? Of the class of a given customer, low risk or high risk. You want to predict that. Now, is this good enough? Meaning that train the machine with that training set and then test the machine on some unseen novel data, unseen novel customer that the machine has never seen before, never trained with before, then the question is this procedure good enough to result in a high-performing machine learning algorithm? It depends. It depends whether the training data that you have used has enough number of samples from both classes, right? You want to teach the machine about two different types of customers, right? So if you have enough number of examples or samples from both classes at hand, then you can hope that your machine has seen enough data from both classes to be able to classify an unseen and novel data with good precision, right? So that is another thing that we will jump in later on, more into detail, probably in later courses. But anyways, the whole idea is that we'll do the training and then we'll actually extract some rule, and then we would basically do the final task, which in this case is the prediction of the class on the novel data. So one thing to remember is that in our example, given a customer, we basically predicted a label, right? So we said, is this guy high risk or low risk? We did not talk about the probability of that customer actually being high risk or low risk, right? So sometimes we're interested in computing that probability, that likelihood, and so that we could have more knowledge about that customer, right? And then basically that would give you much more information regarding that customer. So that is when we use classification through generating probabilities rather than just the class labels, right? And right here you can see that the probability of y given x, right? Imagine that x is the attributes of your customer. It can be the age, the savings, the income, everything that you saw previously, from a customer to a bank, for instance, right? And then you would say that, okay, what is the probability of y given all those attributes for a given customer? Y being the label, say 0 is low risk and 1 is high risk, right? So what is the probability of y being 0 or 1 given the attributes of a customer? So what is the probability that a customer with saving of this much, with the income of that much, with this age, with blah blah blah, being high risk or low risk, right? So basically here you're using classification to learn an association rule that we taught before, right? Now, if I were to tell you that the probability of y equal 1, meaning that the class being high risk given a customer having attributes x is 70%, what would you understand from that? So say this small x includes the age of the customer, it has the saving of that customer, it has the income of the customer, and so on and so forth, right? So you have all these information about the customer who has come through your doors and is asking for money, and before you basically give them the loan, you'd like to measure the probability of this guy being a high-risk customer, meaning y equals 1, right? And if you could, using your magnificent machine learning algorithm, you could say that, okay, the chances of this guy being a dangerous guy is 70%. Then, if I ask you, then, okay, what is the probability of that customer being actually a low-risk customer? Then you would say, okay, since 70% is high risk, then if I say 1 minus 70%, that would give you 30%, which is the chances of this guy being actually a low-risk customer, right? So this would give you more confidence about your customer rather than a simple label, right? So that is another way of thinking about classification. Now remember that probability is always summed to 1, and that is why that I subtracted 70% from 1 and computed the value 30% for the other half, right? So if the probability of a customer, right, being high risk given their attributes equal to some values that I'm going to denote with small x, right? If I want to measure this probability, I can also use mathematics and say that that equals to 1 minus the probability of that customer being a low-risk customer equals 0, given that customer having these attributes, the same attributes basically, right? That is simply a probability rule that they have to sum up to 1. So if you have 1, you can just subtract it from, if you have one of the probabilities, you can just subtract it from 1 to compute the other. So let's focus more on classification. So one of the exciting areas of classification is called the optical character recognition. And basically the idea is that given an image of characters, you'd like to basically recognize those characters, right? Say, consider a handwritten case where people have written loads of numbers and digits and blah, 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 right? So what could be the applications for that? You can basically have a machine that can read zip codes on envelopes. It can read amounts on checks. Especially for the second one, you want to be really, really, really careful so that your machine could do it perfectly. Now, the whole task is, given a character, which class does it belong to? For instance, in English, you have 26 classes because you have 26 letters in your alphabet, right? So if we just exclude numbers for simplicity, given a character, you'd like to figure out whether it's an A, it's a B, it's a C, or all the way if it's a Z, right? Now, what could be the challenges in this case? The challenge is that everybody would write a letter in a different way. The angle could be different, right? The size of a letter can be different from person to person. You can have different handwriting styles. So one can write, for instance, consider letter A, right? If you have a picture of letter A, a picture of a handwritten letter A, right? So some can write it an A like this. Some can write it with some sort of a angle. Some can write it very small. You see my point? So some can have very bad strokes, something like kind of a noise like that, right? On the top, right? Now, here's the thing. As humans, we can easily define all of them as A. We can classify, remember, we're classifying. We can classify them as class A of all the 26 classes of letters in alphabet of English, right? But we can do it, right? But we cannot explain why. We cannot come up with a formal definition of letter A that would include all types of writings of all people around the world who would give it a go and write letter A. We cannot come up with that encompassing rule for everybody on the face of the earth. Now, we are hoping that, basically we know that, that letter A is not just a random collection of strokes. Neither is other letters of English or other characters for that matter. They don't just have a random collection of strokes there. There is a rule there, there's a pattern there that we'd like to discover. And when I talk about that pattern, it's important because a word is a meaningful sequence of characters and letters. They're not independent from each other. So when you read this whole big sentence right here, I'm sure you can read this. So you would say, I'm sure you can read this sentence. So this question mark right here doesn't trouble you at all. Your mind immediately would replace that with I, right? So you would read it as this. You wouldn't find it too much difficult to do that, right? Because there's a grammar, there's a rule in that sentence that dictates the dependencies and order with all those letters, right? So you can easily classify that question mark and that empty place right there as letter I, because you know that, okay, it's missing, but I can figure it out. But you can't just come with a formal definition, probably, for a machine to do that, right? Machine learning can be used to extract such patterns and sequences from the data. So machine learning can see loads of examples of letter A, of all those weird shapes, right? And still classify them as class A, right? As the way that we humans do. So the machine will extract those hidden patterns and classify the characters, the optical characters, in the right way. And that is called optical character recognition. Another very exciting example of classification is called the face recognition, right? So here the input is not an image of a character, but it's a picture of a face. And the output is the identity of the person inside that image, right? In that image. So for instance, here we have 3 pictures of one of the greatest people in the area of deep learning and neural networks. His name is Geoffrey Hinton. I think you might be familiar with him. He's basically known as the godfather of deep learning. Now, consider 3 pictures here. We have many challenges here, right? So an image can have different sizes, right? And the size could be huge, right? It can be a super duper HD quality resolution picture that has loads and loads of pixels inside, right? So it's not just a simple character anymore, right? Or you can have obstacles that would occlude the picture. So here, for instance, you have glasses here, right? That is occluding the face of this person, right? So we can have different colors, right? So for pictures in particular, you could have 3 channels for a picture, meaning RGB channels, right? A picture can be constituted of color red, color green, and color blue, right? And you can have different types of poses of that particular person, different angles. So here the guy is looking to somewhere, probably in an audience, looking at a person. Here he's just looking at the camera, and here he's talking and his eyes are nearly closed, and you have a very different background here with different colors, right? So there are all these, so background challenge, right? So that would beg for certain techniques called the background subtraction as a pre-processing phase before the machine learning algorithm is applied for training and the final testing. But anyways, I don't want to digress. So my point is that face recognition is a far more complicated task than a optical character recognition task. But this is really interesting application of machine learning using classification. So once again, here the input is face pictures, and the output is the identity of the person inside that picture. One more very exciting areas that classification can be applied to is the medical diagnosis, right? So here, the input is the information of a particular patient, and we'd like to classify the illness that that person might have, right? So you might consider just a simple label, like, is it arthritis? Is it a simple cold? Is it cancer? Or you can generate the probability, meaning that, so for instance, with probability 0.20, this person has arthritis, and with the probability of 0.7, the person has a simple cold, and with the probability of 0.10%, the person has, God forbid, cancer, right? And you notice that they sum to 1. If you sum them, you would get 1 as a simple rule of probability, right? So you can either say that, okay, this person has a cold, or you can just generate the probabilities to be, so that you could have a more informative algorithm, basically, more informative rules as well. Now, what could be the inputs of such an application? So you will have loads of information from your patient: their age, their weight, their DNA information, their symptoms, about their parents, about their grandparents, if certain problems have run through the family. They're all important in the diagnosis, right? And you notice that having all those abundant information with all different types of biometrics information and all different crazy types of symptoms that are out there, it is literally impossible for a human being to extract those hidden patterns and rules from that huge amount of data and come up with a very nice and well-defined rule to classify that patient's disease into one of the categories, right? So that is one of the reasons that you have machine learning. They can do this fast and in an automatic fashion. Now, for a patient, you can have in your database, you can have some missing values, right? So the result for certain tests could also be in your data and the attributes of your customer and their information. Now, some tests might be too costly or just simply not necessary for a customer, right? So for those tests, you will have missing values because the customer simply hasn't had those tests, right? So that's one more challenge here. And the major problem here is the cost of a wrong decision, of a wrong classification. Just imagine how ridiculous it will be that if a customer has cancer and you would classify their disease as arthritis, right? They might have some bone cancer, and you would just say that, okay, no, this guy has arthritis. So the cost of that wrong classification is death, right? I don't want to sound dark in here, but to be honest with you, that is very important. We would usually measure the loss and the risks of a wrong classification. I will cover the losses and basically in the loss of a wrong classification and the reward of a correct classification, basically in later courses in different modules, hopefully in the future. But for now, let's just say that it can be disastrous, right? So in the case of a doubt for the machine, right? So if the decision is has this person cancer or not, or they don't have the cancer. So cancer, and we have non-cancer classes. So you have two classes, right? So this is one of the reasons that you would enjoy, you would use probabilities rather than simple class labels. So instead of saying that cancer or non-cancer, you would like to generate the probability of that person having cancer or not a cancer, right? So if you have, say, a 0.50, say 0.51 here, and 0.49 here, so probably 51%, this person has a cancer, and 49%, they don't have cancer. So you see that there's not a meaningful difference between those probabilities, right? So if it was just a label, the machine would have said, okay, 51 is more than 49, thus the person has cancer, right? Now, we do not want that. We generate the probabilities to figure out if it's a case of a doubt or not. Now, this is a case of a doubt. The machine cannot simply just use a magnitude to decide, right? In these cases, we'd like the machine to reject and the decision and basically defer the decision to a a human expert who would study the case in more depth so that we would avoid those disastrous losses about this patient. Yeah, so that is how you would handle a case of doubt. Now, let's come up with let's work on a nice example here in the area of medical diagnosis, right? In this example, I'm going to focus on, not focus, but basically introduce the idea of a confusion matrix, which is a way to describe how well your machine learning algorithm is basically performing. Now, the input into this machine learning algorithm would be the information related to your to the patient, their age, for instance, their symptoms, could be nausea, could be pain in the bones, or whatever. There could be blood in the urine, and their gender, whether they're male or not, and the output would be the cancer or non-cancer, right? And suppose that we have actually trained a model and we have deployed it in a hospital and it's ready to be used, right? And it just keeps working and classifying all the customers per 24/7, and after some time you want to measure how you have done, right? Basically, for instance here, in the idea of confusion matrix, you would have a table, right? Like this. And basically, you can also have this table to basically measure the performance during the training of the model as well. And that is the more common way, actually. Usually they don't do that for the testing, because that's basically on the unseen data. So let's just focus on the more common case, that during training the model, you have many patients for whom you know their class, whether they have cancer or not, right? So each time your system sees those customers, and it makes a decision, right, whether a customer has cancer or not. And then you'd like to measure how well you have done, right? So you have this table right here, and that table is called, or you can also call it a matrix. That table is called the confusion matrix. So here you would have the actual classes, right? And over here on the horizontal axis, you would have the predicted classes, right? So what are the classes? Cancer or non-cancer, right? So I'm going to say cancer with C and no cancer, right? Again, we have here cancer and we have no cancer. Now consider a case where we have 10 patients, right, in our training data, and we use that to train the system. And say that after showing 10 patients to our machine learning algorithm, we will train the machine, right, and so that it would learn what makes a patient one that has cancer, and what makes them a non-cancerous case, right? And say after giving the information of 10 patients to the machine has come up with certain decisions, and then we want to measure how we've actually done, right? So say we have, out of 10, say we have, actually we know that, we have labels, right? We know the truth, that we know that we have 5 cancers patients, and we have 5 none or no cancers patients. So that is the ground truth. That is what we know. That is the truth, right? So say your machine has predicted the case like that, right? So say it has said that, okay, so out of the ones that have cancer, right? So this is the actual case, right? We know that there should be 5 here, but the machine has said, okay, 2 of these guys have cancer and 3 non-cancer. And of the no cancer cases, you know that in actuality there are 5 people in your training data who actually have the cancer, right? But say your machine says, so there's one person who has cancer, and there are 4 of them who don't have the cancer, right? Now, if I want to say that, okay, how we are doing actually here, having seen these numbers in this confusion matrix, how confused are we, basically, if I want to ask that question from myself. So there's a way to analyze this table, right? I will not jump into details because there's a whole lecture on evaluation of machine learning algorithms, right? But here, you know that there are 5 people in your dataset who have cancer, right? And of those who have cancer, your machine has correctly classified 2 of them. You see, this is the predictive classes, right? This is the prediction, basically column right here, right? I'm going to show this column here, right? So of the true cancer people who are 5, basically, you see that your machine has said that, okay, 2 of these guys have cancer, and that is correct, right? So your machine is correctly claiming that 2 of the people in your data set have cancer, but you would have liked it to say 5, but your machine has made mistake because it has said that 3 of the remaining are no cancer people, right? So these are the basically wrong decisions. It is claiming that these people are the no cancer case, but it is claiming it wrong, right? Same story about the no cancer case. You know that there are 5 people in your data set who do not have cancer. And your machine says that, okay, there are four of these people don't have cancer. That is what your machine predicts, right? In this column. But your machine misses one of them and wrongly classifies that person as cancerous, right? Now, if a person doesn't have cancer and you would say that that person has cancer, it is terrible, but it is not nearly as terrible as if a person has cancer and you would classify them as non-cancer, as is the case with this number 3 right here, right? Because these people have cancer and you know that, but your machine is wrongly claiming that they don't have the cancer. So your machine is pretty confused with the cancer class, right? It's doing a horrible job, right? But in the case of no cancer class, your machine is not doing a horrible job, right? Because 4 of them has been correctly classified as no cancer, and only 1 of them has been wrongly classified as 1. So you need to train more and more. Probably you'll need more data. You need to train the system for a longer time. We'll dig more and more into the evaluation process and the whole training, mathematically speaking. But this is just touching the surface to give you some ideas about the fundamentals of machine learning. Hopefully in later modules we will cover all of these ideas in more detail. Right, so some other applications of classification. Right, you can use classification in speech recognition, right? So here the input to the machine learning algorithm is some acoustic signals, or waves basically, and the output is the classes of words that have been uttered, right, using that acoustic wave, right? So you hear some voice of a person uttering some words, and you'd like to basically connect and or associate that signal, that sound, to a word in some language, right? That is very challenging because, again, different people pronounce the words differently. Different genders have different ways of pronouncing things. They have different voices, they have different voice registers. So some are deep, some are high-pitched, or some people have accents. So if you want to basically classify one of the words that I'm uttering, say ask, the verb ask, right? To ask someone something. If you want to classify this word to ask to the actual word ask in English language, again the challenge is that so is it the American English, is the British English, right? So because in British English you would pronounce ask as ask, right? So your machine has to still be able to classify that acoustic signal correctly. And so we have different accents as well, and the people pronounce words with different speeds, and we have different words in a sentence that need to be classified so it means that the input size is not fixed anymore, right? It's kind of temporal. It takes me a longer time to utter a word maybe than say another person, right? So there are all these challenges that you might face in speech recognition, and to be honest with you, it requires a great deal of signal processing knowledge. So if you are someone who's interested in working with speech and voice signals and applying machine learning techniques to it, I must tell you that you will most probably need to study more in depth about signal processing, which could be very well used as a pre-processing technique in your application or in your project. And I don't want to digress, but for those of you who have worked with this before, I would strongly recommend for you to also read a little bit more about deep learning that would kind of, well, not totally, but kind of elevate the need for doing any pre-processing or having any signal processing knowledge for that matter, which would simplify the case. But anyways, speech recognition is a very tricky case of machine learning and basically classification. Right, one more interesting application of classification in machine learning is the biometrics, right? Here the input to your machine learning model is people's physiological and behavioral characteristics. It's a kind of tricky word to pronounce. Anyways, and the output of your model is the identity of that person. Now, the main challenge here is that there are many different modalities of data, right? So for instance, for physiological characteristics, you can think about the face and fingerprint. And basically for the behavioral characteristics, you can think about, for instance, the signature, the voice, so the dynamics of signature, or the gait, or the way a person would walk, right? So there are all different types of data. So one could be picture, one could be basically their voice, which is an acoustic signal. So all types of different challenges are here because of the different modalities that you have in the data, right? Very different types of attributes and features from your from people are available as your training data with your model, right? Now the thing is, there's a very good reason why we use all these different types of modalities from people to basically classify them, for instance, into whether it's an authorized person to enter a building or not, right? There's a very good reason for that, and it's because all of these highly uncorrelated different inputs make the forgery very, very difficult for say a thief or a fraud to basically say break into your security facility, right? Because they might be able to kind of cheat the system with one or two of these characteristics, maybe with your, I don't know, with the face thing. Maybe they can just put on makeup or something, but they cannot easily trick the system with your fingerprint, right? Unless they would cut off your hand or something, or with your with the dynamics of your signature, or with your voice, with the way you walk. So they cannot possibly make all of them right, and break into your facility, for instance, right? So that is a security reason, but the problem is that you will very much inconvenience a legitimate and an authorized user who just wants to get in the building, basically. But you know, security is good. Now, one of the for those of you who have worked with machine learning before, one of the main ways of dealing with biometrics and using classification in biometrics is a mixture of experts, right? And I don't want to digress, but the idea is that each expert would work on one of these types of data, right? Each machine learning model would try to learn one of these modalities. So one type of machine learning algorithm would just work on the images of the face, one would just learn the fingerprint of different people, one would just learn the voice of different people, which is the speech recognition that we talked about before. One would learn the way each person would walk. And then, given an unseen data, meaning an unseen person, someone new, or someone, or anybody basically, it can also be one of the person that we've seen before, right, in your facility. But anyways, given a person, right, each one of those machine learning models would give you their opinion, like the one on fingerprint, that the one who has learned the fingerprints of each and individual person in your organization would say that, okay, 80% I'm sure that this guy is legitimate, this is the person who's claiming to be, he is authorized. And the machine learning algorithm that has learned the images of the faces of the people in your organization, that would give you his opinion, and basically you would gather the votes of different models in your system, and then you make a final vote. Maybe you would just linearly combine them, you would just consider the maximum value, or whatever technique. I don't want to jump into detail, but the idea is that I would use different machine learning algorithms to learn different modalities of data, and then I would use voting to make the final classification decision, as in, is this person legit or not? Are they authorized to get into the building, for instance, or not? And finally, the final application of classification that we're going to focus on is called the outlier detection, right? So basically, you want to figure out if there is an anomaly in your system, whatever it is. So, for instance, if you have a CCTV camera that has been pointed to a street, you want to figure out, you want your machine learning algorithm to automatically tell you if there is something weird going on the street, if someone is walking suspiciously, if there's a stampede, if there is an abandoned suitcase somewhere weird on the road, right? So basically you want to figure out if something weird out of the norm is happening, right? So this is where we're interested in these exceptions, right? These exceptions are called the outliers, right? These are the ones that don't obey the rule. These are the ones that are weird, right? So the rule is learned in order to find these anomalies or outliers. So you can refer to outlier as anomaly, as novelty. So basically, you would see this quite repeatedly in the literature, that the word outlier, anomaly, and novelty have been used synonymously in the literature. Well, they're not exactly the same. Some argue that there are very subtle differences. There are nuances that need to be explained here. But in a big picture, these three words have been used interchangeably in the literature, just so you know. So, what examples can you think of for an outlier? I just gave you an example on CCTV camera. One other very interesting example of this particular application of machine learning is the intrusion detection in a computer network, right? So you have this streaming of data flying through your network, say in your company, and you want to figure out if something weird is happening so that you could avoid or could prevent an attack into your system. Maybe if there's a hacker who's basically getting ready to destroy your whole network, you want to figure out before they would have the chance to do this, right? So that is an intrusion, that is a type of attack, and you want to detect it. And that intrusion is the novelty, that is the anomaly, that is the outlier that you want to know, you want to find, right? So basically here, you would train the system with loads and loads and loads of different types of attacks that are known. And also you would train the system with the non-attack types, meaning that when everything is okay, when the data is normal, there is no intrusion happening, so that you would basically your machine learning algorithm would learn what is normal, what is the healthy condition of a, say, computer network, right? And what is the case where it is being hacked or it's being attacked or there's an intrusion happening. So training with both normal and different types of outliers. For instance, for outliers you can use different types of known attacks that are out there. For instance, the DOS attacks or the DOS attacks, the phishing attacks, the man-in-the-middle attacks. So there are many data packets out there that you can use in your training data to train a better and better and well-equipped machine learning model, right? And there's also an enormous amount of data out there that is related to the normal condition of your computer network, right? So your machine learning algorithm would have learned about both classes of intrusion and non-intrusion, right? So that if something happens in the future, it can classify that. If there's a streaming of data coming, it can classify that streaming of data as either normal, meaning that there's no intrusion happening, or anomalous or outlier, right? So that would give you a hint as to whether you need to be careful or not. Maybe you need to just shut down the network in order to prevent that intrusion or not. Anyways, there are some subtleties here. There are some tricks in here. Not only you would have data from the outliers class, right? Most of the time you have loads of data from the normal class, but not much from the outlier class. But I don't want to digress, but that is generally the case, right? And that is what makes the whole outlier detection task trickier. There are many little like tricky things in here, like many different nuances in here that are hidden, but I don't want to digress and jump too much into detail. After all, this is an introductory course, but later on in the upcoming modules, hopefully I would have the chance to dig more into detail and challenges throughout this whole in machine learning, and while focusing on different areas of machine learning. Anyways, moving on. So we have covered the applications of machine learning in basically learning association and classification. We have talked about different types of them, the challenges that you would have, and coming up next, we will talk about regression, which is yet another application of machine learning. So basically, imagine that you have loads of people, right? And for all of them, you would basically record their income and their age, right? And say that you would come up with a series of data points like this, right? Lovely, right? Then the question is, can I come up with a line that can pass through these data points in a way that it would capture the hidden pattern inside of them, right? So in this case, the hidden pattern is not so hidden, right? it almost seems like there is a linear relationship between the income and the age of people in your data set. So if I were to describe this whole thing with a line, I would say that, okay, there's a line like this that would describe the behavior of your data, right? So the idea is in regression, you want to find that line. But remember that this is a linear regression. Sometimes you're dealing with a more complicated case where the relationship is not linear. For instance, consider the case where there is such a relationship here. Like you have these data points you have recorded in your data set, and then you would go boom, 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 right? And then basically you cannot use any line that would capture the pattern in your training data that has this sort of a shape, right? No line can describe that. You need a curve, right? So you need to come up with something like this, kind of, more or less, right? So this is again a regression, right? This is called finding, this is the regression task, basically, finding the right function that would capture the hidden pattern in your data. But in this case, as you can see, this is not a linear regression. So the question is there just a linear regression out there? So the answer is no. We can have non-linear regression, which is the case that we observed here, right? Anyways, what we're going to learn here is that basically the parameters of these functions that we're going to fit in our data, right? So if it's a line, for instance, in the previous case where we had a simple line, for any line we'd like to learn what are the parameters, right? So if I ask you, like, what is the best line that would go through these data points, right? If the line has a shape of like a line like this, right? How can you describe a line? By its slope and its intercept, right? These are the things that you would need to basically draw a line, right? So if I ask you, if you want your machine learning algorithm to learn the linear regression, it means that you would like your machine learning algorithm to learn the slope of the best line that can fit through your data and the intercept of that line so that you can plot it. And then you can use these fitted curves or lines for the actual prediction of the unseen data in the future. But anyways, I'll focus on all of this more in the next module. In the next class, not the next module. Whew, all right, that was quite exciting. So, our class is done for today. So we covered learning associations and classification, which are two of the most common applications of machine learning. So on behalf of ML Don, I would hope that this has been informative for you. So until our next class, where we'll focus on regression, take care of yourselves and goodbye.